Hi everyone! Today we're going to do some practice with big O analysis. This video is a follow-up from my last video, in which we covered the basics of big O analysis displayed here. In this video, we're going to put our background knowledge to use on some practice problems. Alright, let's jump in and get started. Let's say we're given this piece of code. It takes in an input number n, and then it enters a for loop and prints all the numbers from 0 up to 10,000. This function has a constant runtime. Even though 10,000 iterations is a lot, the runtime does not increase as n approaches infinity. In fact, the runtime does not depend on the size of the input at all. Even if we had a billion iterations, the runtime would still be O of 1, or constant. Another way of thinking about this is we drop constant factors in big O analysis. So we drop the 10,000 and end up with O of 1. Alright, let's take this piece of code. We have a while loop that keeps on iterating while n is greater than 1. And each iteration of the while loop, we divide n by 2. This is logarithmic time, because n is divided by a constant factor in each iteration. Let's move on to this piece of code. We have a for loop from 0 to n, and then a while loop that divides n by 2 in each iteration. The for loop looks like it's linear time, and the while loop looks like it's logarithmic time. But in big O analysis, we drop lower order terms. So we drop the log n term, and we end up with O of n, or linear runtime. Okay, the next one's a bit complicated. What is the runtime of this algorithm? This is called merge sort. It takes in an unordered list of numbers and it returns the list fully sorted from smallest to largest. It first divides the array into two halves, calls merge sort on each half, and then merges the two sorted halves one element at a time by taking the minimum of the front of both halves and tacking that on to the end of the sorted array that it's building. Well, dividing the array into two halves and recursing on each of those halves looks like log n time, since n is divided by a constant factor of 2 during each recursive call. However, merging the two sorted halves looks like linear time, since we do this by getting the minimum of the front of the two halves one element at a time until we have a fully sorted array. So, after performing the multiplication, we get a runtime of n log n. Fun fact, this is actually the best possible runtime of sorting a fully unordered array. Alright, what about this code? We have an outer for loop that iterates from 1 up to n plus 1, and an inner for loop that iterates up to I, the variable in the outer for loop. Let's write out some iterations of this to make sure we fully understand what's going on. So in the first iteration of the outer for loop, I is 1, and the only j that is printed is 0, since ranges in Python exclude the last number. In the next iteration of the loop, I is 2, and j is first 0, then 1. Then I is 3, and j is 0, 1, then 2. This pattern repeats itself until I equals n, and we print j from 0 to n minus 1. So in the first iteration, we're printing one number, and in the second iteration, we're printing two numbers, and so on and so forth until in the last iteration, we are printing n numbers. 1 plus 2 plus 3, etc. until we reach n is an arithmetic series. So we can apply the formula for the sum of an arithmetic series to get n over 2 times 1 plus n. We drop the constant 1/2 in the expression n over 2 and the lower order term 1 in 1 plus n, and then we get n times n, which ends up being O of n squared, or quadratic time. Alright, the next question's a bit interesting. Given a list of potential toppings, this function finds all the possible variations of pizza orders. In other words, we are finding all possible subsets of toppings. Well, for each pizza order, each topping is either 1 on the pizza or 2 not on the pizza. Put another way, each potential topping doubles the number of possible pizza orders, since half of all the possible orders will have that topping and half of all the possible orders will not have that topping. So that's 2 multiplied by itself n times, which is 2 to the power of n. This is exponential runtime, since n is the exponent in our expression. Okay, last one. What is the time complexity of this algorithm? This is a famous problem called the traveling salesman. In this problem, we're given an input list of cities. We want to find the shortest route that connects all n cities, so the traveling salesman can hit his sales goal in the shortest time possible. The only way we can solve this problem is by brute force, so we'd have to find all the possible permutations of the cities. Let's break this down by looking at the order in which he visits a city versus the number of choices that city could be. For the first city the salesman visits, he can visit any of the n cities. But for the second city, he has n-1 choices, since he's already visited the first city and can't visit it again. For the third city, he has n-2 choices, and this pattern repeats itself until he's onto his nth city, and there's only one city left for him to visit. So the number of city permutations is n times n-1 times n-2, etc. until we hit 1. In other words, the runtime is n factorial. Alright, that's it for today's video. We've done practice problems involving all of the most common runtimes. Hopefully this was helpful for you, and thanks for listening.